welcome to my session. Thanks for coming on reacting to the future of application architecture. So over the next hour or so, I'm hopefully going to convince you through a fun and interesting analogy using bees why I think reactive architecture is the future of application architecture. So who am I? Well, my name is Grace Jansen, and I'm a developer advocate from IBM. You'll see a theme here, back in the UK. So I've come over from England today to give you this talk. I haven't always been a developer advocate. In fact, I didn't even come from a software background. I actually did a biology degree. Can't even say the word now. So I did a biology degree, and so I like to take what I learn in the software world and translate it to analogies that I know of in the natural world, so using natural analogies. So that's how I came across translating reactive architecture to bees. So to look forward to the future of application architecture, we have to have a look at where we've come from. So Jansen did a pretty good job of that, looking at our move from monolithic applications to microservices. So monolithic applications were a great strategy when we had small applications not really dealing with vast amounts of data. But when our applications got bigger and bigger and bigger and we had to deal with more and more data, that just became impossible to keep going with. To debug became impossible, to add new features became really hard. And so we moved to microservices, which was a great step forward. And it solved many of the issues we were having, like Jansen described. But there are still issues. I can still go to a website nowadays, try and buy concert tickets, and suddenly find I'm bumped out the queue. I can still go to a website and fill up my shopping cart and find that someone else bought an item that's run out now, so I can't have it. I still go to a website on Black Friday and find that the application's crashing because too many users are trying to buy the new iPhone. There are still issues with our applications, and there are greater and greater and greater demands now from modern society. Modern society and modern users don't expect our applications to crash randomly. They don't expect a worse experience on a particular day for any reason. They want the same experience every single time they visit our applications, and they want that to be quick, fast, and responsive. So how do we deal with these increased expectations? How do we make our applications better for future users? So that's where I turn to bees. So I turn to bees because bees have been around for millennia. They've literally been evolving the behaviors that we want to see in our applications for millennium. And I think we can use the example of bees and the way that they achieve this behavior in our own applications to better suit our users. So bees are this amazingly complex system that seems simplistic when you first look at it. There's loads of individuals all acting towards the greater good of the hive. They all want to make the hive successful. Each individual has their own role within that hive. They have their own purpose, just like microservices within our applications do. But they work towards this greater good of the hive. So I'm going to take you through 3 behaviors that bees show that we want to be mimicking in our own applications. And I promise you it's not just a presentation about bees. I will relate it back to software. So the first of those is food foraging. So as I said, bees have a multitude of different roles and purposes within the hive. And you can be a caretaker bee, a nurser bee, a hive building bee. There's tons of different roles. And one of the roles is a scout bee. Now, the scout bee is a pretty important role. Their role within the hive is to go out and find the food sources for the rest of the bees. So they have to go out and find a flower, come back to the hive, and once they've found a great flower, they come back and they actually make their way onto dedicated dance floors. When they're on these dedicated dance floors, they basically start shuffling their butts around to communicate with the other bees where that flower is and how to get there. So they're able to communicate really complicated factors about these flowers. They can communicate the wind speed that it will take to get there. They can communicate the energy, the amount of pollen there is for them to collect, how great a food source it is, the direction it's in, tons of information. Now, the really important thing is around this dance floor are listener bees. So these listener bees are literally waiting for these scout bees to come back and give them this information. As soon as these listener bees have the minimum information they need to reach that flower, they dash off to that flower. They're extremely responsive in these situations. And that's really important, because if they're not as responsive as possible, and if they don't head off to that flower as soon as possible, they could risk another beehive heading to that flower and basically using up the food source. So it is literally a life or death situation for them to get to this flower first. So bees have to be extremely responsive. And that's what we want from our applications. We want our, okay, maybe it's not a life or death situation, unlike the bees, but we want our applications to be extremely responsive. As soon as my user clicks something, I want a response back to let that user know, like, or I might be computating something, or another page pops up, etc., etc. Our applications have to respond to our users as soon as possible to give them the best user experience possible. The next example is what happens when the queen bee dies. So as I explained, there's loads of different roles in the hive, but there is only ever one queen bee. And she is arguably the most important member of that hive. Her whole job is to produce new baby bees for the rest of the hive. So in order for the population to continue, you need a queen bee. So what happens in the potentially catastrophic situation that that queen bee dies? Well, the hive doesn't crash, the hive doesn't shut down, the bees don't just stop what they're doing as soon as the queen dies. What happens is they have this innate trust in the beehive society that instructions will be put in place to replace that queen. So what actually happens is when the queen is alive, she produces these pheromone signals, and so these chemical signals that the bees are able to pick up on. As soon as the queen dies or is dying, those pheromone signals gradually decrease and disappear. And that's a trigger for the nurse bees who usually look after her to put in place a series of instructions to replace that queen. So what they do is they go and pick about 4 or 5 larvae that haven't hatched yet. They're about 3 days old, and they start feeding them royal jelly. Now this special jelly is what turns them into a queen bee. So the first of those larvae that pops out, she becomes the queen bee. Now, brutally, she goes and murders the others, but it's necessary in order to continue with the hive population and only ever have one queen. So once she pops out, she mates with the drones, and the hive continues. So within 30 days, what could have been a completely catastrophic situation for the hive isn't. They've been able to replace their queen. And what that means is that they're able to be resilient in the face of what could have been a catastrophic failure. They're able to respond to these events in a way that means that their system doesn't crash, doesn't fail, doesn't stop working. They continue because they have this innate trust that that important member of the system is going to be brought back up again. And that's exactly what we want in our applications. We need our applications to be resilient in the face of any potential failure, just like bees are able to do. Now, the third behavior, and I promise this is the last one, is bees at war. So what happens when something tries to attack the hive? So as I said, loads of different roles, one of which that a bee can perform is a guard role. The whole point of the guard bees is to protect the hive. Now, normally, when there's not really a threat to the hive, only about 11% of a beehive are actually guard bees. Now, 11%, when you think about how small a bee is, it's not that many bees. So what happens when something that's larger than this worm comes to attack the hive? So what happens if a bear is trying to come up my hive? 11% probably is not going to deter that bear from trying to get my honey. So what the bees do instead is the guard bees actually go back into the hive, and they're able to dynamically recruit more bees to come and become guard bees. So they elastically change roles from a nurser bee or an undertaker bee or a caretaker bee, and they become guard bees to deal with that increased load on the system. So they stretch the number of guard bees from 11% up to about like 50% depending on the load on the system, and they're able to attack that bee and stop it from destroying their hive. So by dealing with these, they're able to elastically deal with these load increases on their system by elastically changing their roles and responsibilities. And again, that's exactly what we want from our services within our own applications. We need to be building in elasticity into our systems in order to have efficient resource allocation dependent on the loads on our systems, just like bees do. In the case of the beehive, it's the bees that are the resources. In our applications, it's the underlying infrastructure or the microservices. There are loads of different ways to look at it, but we need to be elastic in our architecture of our applications. Now, I promised that this related to software, and it does. So has anyone heard of the Reactive Manifesto before? A few hands going up. Great. OK, so you can probably see where this is going. So each of the behaviors that I just described actually maps really well to the Reactive Manifesto. This was a specification that was designed back in 2013 by a guy called Jonas Bonner and a few other colleagues. So what it is it's a specification to lay out how you build a reactive application. There are lots of implementations that have been built from this specification, but there are 4 main key cornerstones that make up the manifesto, and they relate to the behaviors I've described. So the first of those is responsiveness. So if you want to achieve a reactive application, you need to be as responsive as possible. You need to be responding to events or loads on the system as soon as possible. And again, that's exactly what we see in bees and in bee society, and we need that from our own applications. But how do we achieve responsiveness? Well, we need elasticity. Like I described, the bees are able to elastically change their roles from being any random role into guard roles based on the load on the system. And we need our resources within our own applications to do the same thing to deal with these differing loads. So elasticity enables us to be responsive because we're able to dynamically change those resources to respond to events in our system. We also need resiliency. So if our system fails and crashes because one service goes down and we haven't decoupled properly, we're not going to be responsive because our system is down. So we need to be both elastic and resilient in order to achieve responsiveness, in order to achieve a reactive system. But how do we achieve resiliency and elasticity? Well, it's all underpinned by one thing. And if you can't tell from my cartoon, it's being message-driven. So bees are naturally message-driven. They're able to communicate on both a one-to-one level and a one-to-many level with the other bees using asynchronous messages. And the asynchronicity part is really important as well. By having asynchronous messages, it allows us to completely decouple services within our application and decouple the need for a bee to stay to listen to a response, for example, in the beehive. So when we took the example of the guard bees coming in, those guard bees don't go up to an individual bee and say, "Hi, I'd like you to become a guard. What's your response?" No, they just tell them they need more guards, and they know intrinsically that eventually they'll get a response from that. When the scout bees come back to the dance floor, they don't wait for those listener bees to tell them they've heard them. They just display the message about where that flower is, that food source is, and they know that these other bees will react to that message. So it's all about being asynchronous and message-driven. So why do I think that reactive architecture, based on the Reactive Manifesto, is the future of application architecture? Well, those bullet points I just showed, those cornerstones, they seem to match pretty well to the expectations that these new users have. They seem to be trying to solve the issues around applications randomly crashing, not having applications that respond to the users, and solving the issues that our microservices currently don't solve. So how do we go about using reactive architecture? Well, what I'm describing in this presentation is a reactive system. There's a difference between reactive programming and a reactive system. Has anyone heard of reactive programming before? Yeah, a few more hands. Yeah, it's usually the one people have heard of. The mistake comes when people assume that by implementing reactive programming in their applications, they're building a reactive system. The two go hand in hand, but aren't exclusive. So if I describe it in the case of bees, so let's assume you've got a bee soccer team. So we're playing football here. Anyone a football fan? A couple of hands? Great. 2 hands at the back. Keen. So imagine you've got a team full of Lionel Messi, arguably a really good player. So let's assume that this individual is the best scorer or the best tackler or the best at dribbling it up the field. Individually, that player is awesome. Individually, that player is really good at reacting to the events around them and reacting to what's happening on the field. As a team, however, they've never played together, they might be a bit selfish, they don't necessarily know how the others are going to react to events that they cause on the field. If one of my individually amazing players kicks it up the field, they have no idea how the others are going to react. So between the components on that field, between the players, there's no reactivity. That's reactive programming. Reactive programming is a really great method of trying to make the internal logic within a microservice reactive. It's all about the internals within the microservice. It doesn't cover what happens between the components in a system. Nowadays, our applications have multiple microservices, many microservices, and it doesn't cover how to create a reactive form of communication between those components. Now let's look at the other side. Okay, let's imagine a team that, okay, maybe they're like middle-of-the-range players, they're not the best of the best, but they've been playing together for over 30 years. So they know exactly what the other members of their team are going to do. They've got set plays in place. They know what the others are going to do when they do certain events on the field. They know how they're going to react. That's great, but imagine if you could combine the two. Imagine you had a team of Lionel Messis who'd played together for 30 years. You'd have the ultimate team, and you'd have an amazing team, and they'd be individually reactive as well as reactive as a system, as a whole. And that's what we want to achieve with reactive systems. We want to use reactive programming as a tool to create better reactive systems. But you have to be thinking about the component, the parts in between the components, not just within your microservices. So how do we enable these reactive behaviors? I'm sorry, I couldn't avoid one pun. Please don't help me for it. So I'm going to take you through some commonly used frameworks, toolkits, and methodologies in order to create reactive systems. This is not a comprehensive list. If it was, you'd never go home. So I've just picked a couple of commonly used ones, and these aren't exclusive to reactive. This isn't a reactive-only club. These can be used elsewhere, and you might already be using some of them. But they're useful in order to create an application that sticks to the reactive specification, the Reactive Manifesto. So the first of those is domain-driven design. Quite commonly known, and usually most people at conferences like this have already heard of it. But if you haven't, domain-driven design is all about splitting down. It's a great technique to use when you're trying to split down monolithic architectures into microservices, for example. So domain, that stands for just a sphere of knowledge. So it's breaking down your application into those different spheres, those different domains, those different business areas, for example. Driven design simply means you're driving the design of your application based on those different domains that you've identified. So with the example of bees, I've already picked out the different domains. So you start off with a baby bee. That baby bee can become one of three things. It can either become a queen bee, a drone bee, or a worker bee. Queen bee, the one who produces all the baby bees. A drone bee, they're the males. They literally just replicate and then they die. And then you got the worker bees. So the worker bees are the females in the hive. Now, that's where things get interesting. So a queen bee can't do what a drone bee does, a drone bee can't do what a worker bee does, and a worker bee can't do what either of the other two do, and vice versa. So each one has its own individual domain. They're good at a particular thing. The worker bee is where things get complicated. So it's the worker bee, the female bees in the hive, that are able to split down into the different roles. So if you think about the worker bee, the generic worker bee, as being the aggregate root for that domain, they have a ubiquitous language, which means that they all understand what the others do, and they're all able to switch into the other roles. That's how we're able to elastically change the bee role from a nurse bee, for example, into a guard bee, because they have this ubiquitous language and they're all part of the same domain. This is just one example of me breaking down bees. Obviously, it's different when you're looking at an application, but domain-driven design is a really great technique to do that if you haven't already split down into microservices. So ubiquitous language is great within each domain, but what happens when we're trying to communicate between domains? Well, that's where asynchronous communication is really important. Without having asynchronous communication, you're going to have blocking at some point. Asynchronous communication is all about separating out the different components of your system and ensuring that you don't get these bottlenecks or this blocking. So let's assume that bees aren't asynchronous, which they are. Let's assume they're not. So let's assume that when they're trying to put the pollen in their hive, they have to wait for the bee in front of them to dump it first before they can go in. So suddenly, instead of being able to have multiple bees going in and out of the hive at the same time, you've now got blocking and you've got a queue forming outside the hive. You've got wasted resources now. And that's just a waste of resources. You're not effectively using those resources as best you can. So bees actually already have this in place where they can have multiple bees going into the hive to stop those resources being wasted. Now, this is super important to have asynchronous communication now especially, and to stop that blocking, because where we previously had a data at rest sort of scenario, we now have data in motion. So where previously it was okay for us to do batch processing overnight and for us to react to data in a fairly slow manner, That's not okay anymore. We're expected to be reacting to data as soon as it comes in, as soon as those events are made. We're in this data in motion scenario. So it's not okay anymore to do batch processing. So how do we respond to events or to data as it comes in? Well, one commonly used tool is event sourcing, and it's often used with CQRS. So event sourcing is essentially where you store a log of events. And an event is essentially a state change to that system. So instead of storing the actual data itself, you store this log, which means that if your system crashes, you can just read back over the log of events that have happened to the system, and you can reinstantiate your microservice or your system back to what it was before by following these steps. Now, it's often used with CQRS, as I mentioned. So CQRS stands for Command Query Responsibility Segregation. In layman terms, that just means you're separating your read and write databases. Now, this is actually pretty similar to the natural world. What it means is we have extremely high availability because you're able to read those read databases whenever you want, essentially. Now, bees already do this, just like you and I. So we all have a brain, and in that brain, we have our own read database, just like the bees do. So the bees have their own version of the state of their world or the state of their system. So if you look at the dancer bee, so you can imagine the dancer bee is actually writing to each of the read databases, each of the brains of the listener bee. And those read databases are being updated with where the new flower is. Now what that means is, in the case of a bee trying to find the flower and suddenly it gets knocked off course, it doesn't have to go all the way back to the hive and ask that bee again, where was that flower you mentioned? Instead, it just looks into its read database, checks out its brain, finds out where the instructions were, and it can re-navigate to find that flower. So that means that it's able to respond to those events really quickly because it's got high availability. But with high availability, you do have to compensate based on the CAP theorem, which I'm sure many of you guys here have heard of, but if you haven't, check it out. It's essentially a theorem that explains that out of 3 characteristics, you can only ever optimize 2. And in this case, we're optimizing availability, but that means we have to compromise on the consistency. And that's okay. Most applications do compromise on consistency, and they prefer to try and have high availability. Because actually, that's the way that we work in this world. So if I, for example, update your own read databases and actually tell you, I didn't draw any of these diagrams, instead it's my mum, your state of the world has been updated. But everyone else out there isn't consistent with the state of the world. They're eventually consistent. Now, you might go out and tell your mate that, oh no, she doesn't draw any of those, it's actually her mum who draws them, and you'll make them eventually consistent. So it's actually how we work in the modern world. We are all eventually consistent beings, so it kind of makes sense that our applications are as well. So in the case of the bee, let's imagine that with this high availability, like I said, if a bee goes wrong, they can revisit the data and they can navigate back to where they're supposed to be going. But what it does mean is, if the last bee who went to that flower discovers that there's no more food left and no more bees should go, they have to come back and update the state of the system, update the state of the hive. So what they do is they actually headbutt the other dancer off the dance floor. It's a pretty clear signal that there's no more food left. And what that means is that any listener bees that are still around the dance floor, they're able to update their read database. They're able to know, oh, I shouldn't go to that flower because there's no more food there anymore. But what about the bees that have already flown off to that flower? Well, they're going to be on a wasted journey because they're going to get there and find there's no food. They're not consistent with the state of the hive. But that's okay, because it's only going to be a couple of bees. So although they'll be wasted resources for a short period of time, they will eventually become consistent. There are tools that we can put in place to improve this consistency. And one of those is sharding. So there are different kinds of sharding. There's akka sharding, which is part of the akka framework. I'm talking about database sharding. So if you really have to use a database, you can use sharding to improve the parallelism within your database without causing collisions. So in the case of bees, let's assume that they don't use sharding. Bees actually kind of use a form of sharding, because if you imagine the honeycomb structure of a beehive, that honeycomb structure allows multiple bees to put in their honey at the same time, without colliding with each other. Now let's assume that instead of that amazing honeycomb structure, instead you've got one massive vat of honey, kind of like Winnie the Pooh. So you're having to fill up that vat one at a time. Again, you've got blocking, you've got wasted resource, when you could have each bee going to their each individual cell. So sharding and database sharding allows us to split up a large database into little pieces. That's essentially what a shard is, a little piece of a whole. And it enables us to increase the parallelism without locking and without blocking and without collisions. So sharding is a really great tool to help with that, and bees already do it. Another useful tool that we often use is back pressure. Now, back pressure is a form of feedback or flow control. It's essentially where the subscribers to events or to data can't keep up with the publishers. And it's a way of communicating the fact that they can't keep up and the fact that they need to slow down. Now, let's imagine the case of bees. Let's say that we've got too many scout bees coming back with honey ready to fill up the hive, and we haven't got enough bees making the cells that they need to fill up. So instead of having this queue forming, wasted resource, blocking, a potential bottleneck, wouldn't it be great if we could have our hive building cells communicate with the scout bees and say, whoa, slow down a minute, I can't keep up. Or say, guys, can one of you come over and help us build some more hive cells? Then we wouldn't have the blocking. So by communicating this through feedback, they can stop the number of bottlenecks they have and the amount of blocking that happens in that system. So it's a really important form of communication that's useful if you don't want to cause as many bottlenecks. What I like to think of as kind of the opposite is bulkheading. So bulkheading is essentially where it's the publishers of events or of data that limits the amount of data or amount of events going to the subscribers. So it's kind of the opposite way around. Again, it's a form of flow control and feedback. It's to help prevent resources that are overloaded or under stress from breaking, essentially. So in the bees, again, they already do this. They're amazingly great at this. So if we go back to the example where you've got the scout bee dancing for the listener bees, now that scout bee is already determining how many bees should go to that flower. They're already trying to calculate the limit of the amount of information that they share with those bees to determine how many of those bees should go to that flower to collect the pollen. And that's because they know that the number of bees in their hive is limited. They themselves are the limited resource. And if they send too many, they'll waste those resources because they won't all be able to collect pollen. If they send too few, they'll waste the limited resource of the flower. So it's a delicate balance between the limited resources that they have between the bee and the flower. So they're able to use bulkheading to basically prevent them from wasting these resources or from these resources becoming overloaded. Another tool that we use to protect limited resources, commonly in Reactive, is circuit breaking. Now, bear with me with this example because bees are intelligent beings and software is not. So in the software example, it kind of relates, but with the bee example, they're able to self-diagnose it, and we currently don't with software. So when a bee gets sick, just like you or I, they're able to self-diagnose that they're not performing to the standard that they should be. They're ill. So to protect both themselves and the rest of the hive, they actually remove themselves from the hive. So they take themselves away. That A, stops the spread of that disease or that illness to other members of the hive and stops it from completely destroying the bee population. But it also gives them a chance to recover. It gives them a break from the work that they were doing so that they can hopefully get better. And when they do get better, they're able to rejoin the hive and continue doing the role that they were doing. Now, we kind of do the same thing in software. So circuit breaking in software is a little bit different because they don't self-diagnose the fact that they're not working very well. But by having parental microservices or parental actors, we can basically keep an eye on our child services or child actors and determine if I keep seeing the same error message coming from my microservice, maybe it's not responding very well and maybe it needs a break. So by circuiting around that microservice and giving them that break that they need, you give it that chance to recover and to then basically get through its backlog so it can then perform the role it was doing before at the rate it should be. So circuit breakers really help us to stop resources from becoming bottlenecks and potentially breaking our systems. So that's kind of the last tool I was going to take you through. As I said, not a comprehensive list, and each of these could be implemented individually if you wanted to. But by combining these tools and others, you can hope to create a reactive system. Now, you can do this yourselves if you want to, and you can go out and find out how to implement each of these individually, or you can take an easier route out of it. So there are tons of open source frameworks out there that enable you to create reactive systems. They do that in different ways. So you've got Akka, Play, and Lagom. These 3 frameworks are made by a company called Lightbend, and they work off the actor-based system. You've then got Vertex, which is made by Red Hat, and that doesn't work off the actor-based system. That works off a system called Verticles, which I'll go through in a minute. You've then got RxJava, which was originally made by Netflix. It's now been open sourced. You've got Spring Reactor. So if you're already building a Spring application, for example, Spring Reactor might be a framework that you'd like to look into, or MicroProfile. So if anyone was in Emily Zhang's talk earlier, she mentioned about MicroProfile. So does anyone know what it is? Hands up if you do. Yeah, a few hands. Great. Fantastic. For those of you who don't know what MicroProfile is, it's an open source framework to basically enable you to build microservice-based architectures using Java EE. So it enables you to have implementations like fault tolerance, health, metrics, and a bunch of others. And they've just introduced reactive messaging and reactive streams. So these have been introduced as well. Some of these are end-to-end solutions. So for example, Akka is actually an actor-based framework. Play is for their front-end and web development. And Lagom is their opinionated microservices framework. So by using all 3 and a couple of other tools, you can actually create an end-to-end solution. Others are individual components that you can use to create a reactive system, but aren't necessarily end-to-end. So what's the difference between the different models I was talking about? Well, there's the actor model. So this was actually made by a guy called Carl Hewitt back in the 70s. But it wasn't until recently that we started picking it up as an implementation, mostly because of the resources that we had available. So the actor model is actually a conceptual model, to deal with the concurrent computation. So it's based on actors. So actors are sort of a granularity level below microservices. So you can have multiple actors per microservice, or you could have a one-to-one mapping. And an actor is essentially their unit of computation. So you can kind of think of an actor like a computational function. So you can call these actors using their message queues, essentially. So you send a message to them, they work through those messages one by one, and whilst they're waiting, their messages get stored in this message mailbox, essentially. There is a difference. So actors use a hierarchy, whereas microservices tend not to. So actors tend to have parent and child microservices, and that enables monitoring of those child microservices, and it enables things like Akka clustering and Akka persistence. If you want to know more about that, I can talk to you about it more later, or you could look it up on the Akka framework website. They also are language specific. So you have to use either Java or Scala. Originally, Akka was actually written in Scala, but they've now created Java APIs for it. But you have to use either Scala or Java. And it is only it gives you at least once delivery, whereas microservices give you at most once delivery. So that's a benefit of using the actor model. Now, as I mentioned, there's a different model you can use, and that's Verticles. So this is what Vertex is built upon. So Verticles, in this scenario, Verticles are the unit of execution, and it's essentially an event loop. So in this case, they don't have a hierarchy like with actors. They have a flat hierarchy, so they tend not to have parents and children. They, however, are language agnostic. So you can use it with Ruby, Python, but you can also use it with Java and Scala if you wish to. So they're language agnostic, so if you're favoring a particular language, it might be better for that. But it does not enable at least once delivery. This form is actually at most once delivery. So if you, for example, are working in like the banking industry is a good example, and you need the at least once delivery, you might want to go down the actor route and use Akka. The only problem is it can be quite a different, it's kind of a paradigmal shift in the way you have to architect your application. So if you're already using microservices, you might want to look at things like Verticles and Vertex. If you're on a monolithic application, or you are confident that you want to use actor-based systems, and you're okay with spending those resources and re-architecturing, actor-based systems can increase the resiliency of your application, but it does require quite a fair bit of re-architecturing. They're the 2 main forms, the different patterns that you can use to create reactive systems currently. So why do you even care? What difference does this make? Why would anyone want to go to be a reactive system? Well, I've given the example here of Verizon. So Verizon actually came to us with their own monolithic application. So this application was their website. It was both a web app and a mobile app. Now, the issue they had was that their application was not dealing with the loads that were being put on it. So for example, on Black Friday or the release of the new iPhone or the new Huawei, it was not dealing with that load the way it should have done. So basically, because it wasn't able to deal with these increased loads, they actually had to shut down parts of their system to even begin to deal with it. So that meant that other customers trying to access their account details or trying to top up their own SIM cards couldn't do that because they were having to shut down those parts of the system. It's just not acceptable in modern society. As a user who's paying, you expect to be able to access the resources that you need to whenever you want. So what they did is they came to us and they said, right, we'd like to change to be both microservices but also reactive, because we want to be able to be as responsive and resilient and elastic as possible for our users to get the best user experience. So as you can see, it was really important that they did this because actually most of their interactions were digital. They weren't in store. So 88% were digital, and out of those, almost half of their sales, their digital sales, were from their mobile devices. So it was really important that they improved their application, and it actually achieved some fantastic results for the company. So these are the facts of what happened when they moved from this monolithic application architecture to reactive microservices. So they were able to have their page response time decrease, and that meant that they had their conversion rate go up. So their conversion rate of people hitting the website and actually buying something at the end. Now, there's been loads of studies that have been done by Google, Cook, Pinterest, and a ton of other companies where they've shown there is a direct relationship between page response time and how long it takes for a page to respond to a user and conversion to sales or conversion to the number of people visiting those websites or visiting those pages. Happy customer is when you get a quick response and they can use that website easily and without frustration. And that's what having a quick page response time enables. They were also able to importantly use 1/8 of the infrastructure. That's a huge decrease in infrastructure, which means that there's less things to go wrong, less infrastructure to monitor, and less cost in that infrastructure. Not only that, though, they're able to decrease their deployment time hugely, from 4 to 8 hours to 30 minutes. Now, that's a huge impact on the developers. So it wasn't just the customers who benefited from this, but it was also the developers who made it. The developers ended up being 20 to 40% more productive. That's less frustration for the developer and a big thumbs up from those who have hired them, because they're getting more out of those developers than they did before. And those developers are happier because they're able to work on it more productively and have this lower deployment time. And their order completion rate also improved, which, again, led to more sales. So you can see it can have a real business impact. Now, there are other examples. If you want to take a look at industry-specific examples, there's a whole area of Lightbend's website where they take you through different examples, including PayPal. There's a couple of other, there's some big names in there, Walmart, for example, and they take you through how they've migrated them onto a reactive system and what business impact that's had. But why do you individually care? You're not PayPal, you're not Verizon, you're not Walmart. What difference does it make to you? Well, if your application cares at all about being elastic and having cost-efficient use of those resources, if it cares about being resilient in the face of any potential failure, regardless of what that is, and if you care about having a responsive application that enables the best reactive response times to your users to enable the best user experience, well, reactive might be for you. You might want to consider reactive architecture in your own application architecture. So how do you go about doing this? I've kind of just spurted at you all this wonderful facts and why you should move to reactive. What can you actually do to get there? So there are tons of resources out there. There's loads of O'Reilly books, literally written by the guys who made the Reactive Manifesto. So there's a great one done by Jonas Bonner. If you want to check that out, it's free online. I've been kind of biased with the ones I put up here. I do work for IBM, so I kind of have to put our blogs up. But there are tons of others other than IBM if you don't necessarily want to look at ours. I would recommend one particular blog that we have done, though. It's a blog series in 12 parts that takes you from a monolithic application through to breaking it down into microservices, through into turning those microservices into reactive microservices. So it's a real step-by-step guide as to how to convert your own application into being a reactive application. We use an example of this. We use a stock trader example application to lead you through this. All of the code is on GitHub. It's all open source, and you can take a look if you want to. It is in one of the resource slides that I have. But there are courses online if you want to do a course rather than looking at code. So Lightbend have done a great course on Coursera, which you can do, which takes you through what Reactive is, how to achieve it, how to convert your own applications to it. So this is the slide that I would recommend you take away from this talk. These are some of the useful links that I think are useful when trying to implement Reactive. So if I haven't convinced you in this talk that you should move to Reactive, there is actually a Why to Move to Reactive in Less Than 12 Minutes blog. So if you only have 12 minutes, please read that one. But otherwise, if I haven't, so for example, I put the Reactive Manifesto up there. So if that wasn't clear from my B diagram or any of the other diagrams I drew, you can visit that website and they take you through each parts of the specification, each of the cornerstones. And there's also a really useful glossary of terms if you didn't understand anything in this talk or you want to look up any particular terms yourself. The second one down is that blog I described, the one that takes you step by step through to being a reactive application. The third one down is just kind of, again, another, if you've got more than 12 minutes, another why you should go reactive link. I've also linked to 3 of the frameworks I mentioned, so Akka, Lagom, and Vertex, if you want to check those out or check out the specifics behind it. So the difference between Acta and Verticles, for example. And the bottom one is the CAP theorem that I mentioned. If anyone hasn't heard of it before, that article is a really great description of what it is and why it's important and how you can optimize. So thank you very much for listening. I hope I persuaded you that if bees can do it, we can do it in our own application, and that maybe Reactive is the architecture for you. Thanks very much.